Hello, physics students. This is Dr. Brenzy. I wanted to go over problem number 4 in lesson 5.2.6. I briefly showed this to you at the end of class, but it was pretty hurried and it was near the end of class. So I rushed things a bit, and I'm pretty sure that a lot of us may not have gotten all the information that we needed to solve this problem. So I thought I'd create a video and help you out. So this is a diagram of our problem here, and as I said in class, we've been used to assuming that the mass of this pulley is 0. So we ignore the mass of this pulley. And what that does is that allows us to say that all of the gravitational potential energy that comes from this mass dropping will be put into moving this mass in this mass over here. But when you have a mass on this pulley, now some of this energy that was gravitational potential energy from this being at a certain height. So the gravitational potential energy that will give us our kinetic energy, some of that has to go into rotating this pulley now. So we're going to lose some of the energy that we would have put into moving this block and that block. So let's consider first the block that's on the table, M1. And if you remember way back, what we did to solve pulley problems like this is that we drew a free body diagram of each of these masses. So we have this mass, M1, the one that's on the table, being pulled by a force, a tension force that I called F1. And that's the only force that's acting on this mass in the horizontal direction. Of course, we have gravitational force and normal force, those balance out. But in the horizontal direction, all we have is this tension force. This box is going to accelerate to the right because we imagine that the other box is going to pull it in that direction. So it's really important with pulley problems to keep track of the direction of acceleration because that tells us what signs we need to use in our equations. So if I write out Newton's second law, F net equals ma, and the net force is just going to be the tension force, F1, and that is going to equal the mass of the block times its acceleration a. And that's as far as we can get with this problem. So let's now consider the other block, M2. It has a gravitational force pointing down, and it has a tension force pointing up. But unlike what we've been used to, this tension force is actually going to be different than the tension force I had in the box on the table. The reason that is because if the tension forces were the same, it would turn out that there would be zero torque on the pulley, so the pulley wouldn't rotate and we wouldn't be moving anything. So if our pulley has mass and we have to consider that mass, then it has to also be true that this tension force, F1, pulling this mass, has to be different than F2, which is the tension force holding this mass up. In addition, one of the other things we had to keep track of, like I said before, is the sign of acceleration. Now, we would expect this mass to accelerate downward, which means that it's going to actually have an acceleration of negative a because that is the negative y direction. So when I go to write Newton's second law, F net equals ma, and I start substituting, well, I have net force, which is just F2 minus Fg, and Fg is just m2 times g. That is going to equal negative, because I'm expecting my acceleration to be negative, negative m2 times a. So that's the second equation that I can set up to solve this system. Well, in the past, we've been used to this equaling that, so we would only need two equations because we only had really two unknowns. It was the tension force and the acceleration. All the other things were given to us. But now that these tension forces are different, I now need a new equation in order to solve this system. Well, that new equation is going to come from our pulley. So here's a big version of the pulley. We have the rope going around this pulley, and this tension force is going to be F1 pulling in that direction. We have a second tension force, F2, pulling in this direction. And let's draw the direction of those forces. Now, because this is a pulley in rotational motion, I now have to write the Newton's second law for rotation instead of for translation. So now I have tau net equals I times alpha. Well, let's figure out what the net torque is. The net torque is equal to the torque due to this force, which is equal to R, the radius of my pulley, times F1 times sine of theta. Well, this tension force is acting where the pulley first meets the string. And that happens to be right here at a 90-degree angle, well, right at the very top. So the angle that's formed by my radius, which would be an imaginary line going here, and my force, that would be a 90-degree angle. So sine of theta is going to equal 1. If I find the torque due to this force right here, I would do a similar thing. It's going to act at the same radius. It's going to have a different force, F2. And just like we had for F1, we have this force acting right at this this point right here, which is perpendicular to, so the force is perpendicular to the radius again. And so sine of theta 2 is going to equal 1 again. And now I have to consider which torque is going to be positive and which torque is going to be negative. Well, this force up here wants to move the pulley in a counterclockwise direction, so this torque is going to be positive. This torque, on the other hand, is going to want to move the pulley clockwise, so that torque is going to be negative. So I need to put a negative sign in front of this one, and so I have net torque equals RF1 minus RF2. So let me go ahead and write that out. RF1 minus RF2. I can factor out an R out of both terms. So I could just write this as R times the quantity F1 minus F2. Well, let's plug that back into my Newton's second law for rotational motion. So now I have R times quantity F1 minus F2. And that's going to equal I times alpha. Well, what is I? It is the moment of inertia of the pulley. Now, there are two types of pulleys you can have usually. One is usually a solid disc, so its moment of inertia is 1/2 mr squared. And then sometimes you can have these pulleys that have spokes on them, and we can treat that like a bicycle wheel or a loop. So its moment of inertia would equal mr squared. Now, I didn't explicitly tell you this in the problem, but as I looked on that diagram, I noticed that the pulley was filled in. So I am actually going to use this moment of inertia in the video. I didn't remember that fact in class, so I actually used this one in class. So if you actually took pretty good notes and are just confirming, just realize that I am now going to use this moment of inertia here in the video. So let's go ahead and write that moment of inertia in for my value of I. And so I have R times quantity F1 minus F2 equals 1/2 mr squared times alpha. Well, forgot to write that left-hand side there. There we go. Now it's complete. Now, let's think about which direction this pulley is going to go. Remember, we have mass M1 over here, and it's going to want to move, it's going to want to accelerate toward the right. So this point will be also accelerating toward the right. So it's going to be accelerating at the same rate which our block is. Likewise, right here, this point is going to be accelerating downward just at the same rate. So that acceleration is going to be A. And the acceleration of this point right here is my tangential acceleration. And if you remember the formula for tangential acceleration is equal to alpha times t. So these two accelerations, they are going to want to cause this pulley to accelerate in a clockwise direction. So we can say that this angular acceleration alpha is a divided by r, because tangential acceleration alpha t is equal to alpha times r. Now, because this is rotating clockwise, or this wants to accelerate clockwise, alpha has to be a negative value because clockwise acceleration is negative. So that's why I have to put a negative sign out in front. So now let's replace alpha with this quantity right here in our equation. And so we have r times the quantity F1 minus F2 equals 1/2 mr squared times negative A divided by r. We can do a little simplifying right here. We get 1/2 times m times r times A. Don't forget the negative sign. I put this negative sign out in front. That one right there. Right. So now I have r times quantity F1 minus F2. And now I notice that I have an r on this side of the equation, r on that side of the equation, so I can divide both sides by r. When I do that, I get F1 minus F2 equals negative 1/2 m times A. Well, that's as simple as I can make it until I start knowing some actual numbers. So let's go back to our big picture here. We came up with an equation for M1, this mass, this block right here, and it turns out that that equation was M1 times A, or F1 equals M1 times A. I came up with an equation for this block right here, and it turns out for that block we had F2 minus M2 times G equals negative M2 times A. And then we ended up with an equation for the pulley. We found that F1 minus F2 equals negative 1/2 m times A. So now we have three equations. So we have a system of three equations. And if you're curious about how to solve a system of three equations, well, you can always use substitution. We already know that we can replace F1 with M1A, so I'd plug that into there. And then you might want to solve this equation for F2, plug that into there. And then you can solve for the acceleration of the rope, or the acceleration of the system. The acceleration of this block, which is the same as the acceleration of that block, which is the same as the tangential acceleration of the pulley. And from there you can figure out anything else you need to know, like the tension force here and the tension force there. Alright, hope that's a helpful video, and I look forward to seeing your answers tomorrow. Bye.